Hi everyone. Today I'd like to quickly go over rebuilding the 64-bit Linux kernel for a Raspberry Pi 5. I am in the need of building some custom options into the kernel to support a BTRFS file system for a project I'm working on, and thought I would make a quick video describing how to go through the kernel building process. It's not very complicated if you just follow through the procedure. So with that, let's take a look at the hardware that I will be using. So we've got the Raspberry Pi 5, and this is the 8 GB version. If you can, I would recommend getting the highest RAM quantity in the Raspberry Pi if you can for anytime you're building software on it. If you do run into RAM limitations, you may run into problems with the compile. So I do recommend the 8 GB. I mean, you can do this on the Raspberry Pi 4 also, although the Raspberry Pi 5 will probably be quicker. So I've got while optional, I went ahead and opted for the Raspberry Pi 5 case. This is the official case. It's got a fan on it, and you'll notice that I've also put the heatsink on top of the CPU. And when building the software on the Raspberry Pi 5, the Raspberry Pi 5, normally you put your software on the SD card, and the SD card, the write endurance on a lot of these SD cards is extremely low. I would highly recommend going with some other storage solution while you are building software on the Raspberry Pi, or you may burn out the write endurance on your SD card rather quickly. So in my case, I'm going to use I've got a 4 TB hard disk that I put in a case, and it's just a USB 3, 3.1, 3.2. So it's a USB 3 hard disk. And I will be connecting this to the Raspberry Pi to use it as an external storage device when I do the kernel building. So with that, I'm going to prepare a fresh Raspberry Pi OS image on an SD card. The method you use to prepare this image, there's multiple ways to do it. I will go through the process doing it on a Linux computer very quickly. And then once the SD card is prepared, the rest of the process will be performed on the Raspberry Pi itself. So with that, let's go to the computer and we will write the SD card image. While not entirely important, the SD card that I've chosen to use for a lot of projects is this SanDisk 64 GB Extreme Pro. I've had a lot of good luck with these SD cards, and they do still experience the write endurance problems that I described previously, but you'll get that with any SD card. But I find these SD cards to work extremely well and are extremely snappy and run things rather quickly on the Raspberry Pi. For the actual writing process, I've got a USB to micro SD card adapter. This will allow us to write the initial OS on the Raspberry Pi. So with that, let's connect this into the Linux computer and we'll write the image on the SD card. Okay, once we have downloaded our image that we are going to write, we have connected the SD card to the computer, and now we need to figure out what device we need to write to. There's a couple ways to do this. We could do a D message, and if you look down at the bottom of the output, we'll notice that the last device connected, we've got SDC, attached generic SCSI generic, and this is actually SD card, and we'll notice it does have 2 partitions on it because I've used this SD card before. Another way that we can find out what we've got, we can do an ls/dev, and depending on your Linux installation, you may or may not have a lot of devices showing up here, and we'll notice we have SDC2 showing up here. And if we want to shorten this list and make it a little bit easier, we can do an ls, and we can SD with an asterisk, and this will filter to only show the SD entries. And we'll see we have SDC, SDC1 and 2. Another way to quickly see the output on the information on the device we connected is we could use fdisk, and we'll provide the device, and this will output. So change that so it's more readable, and we'll see that the device, this is a 64 gigabyte, close to 64. This is a 64 gigabyte SD card, so we know that we have the correct device on SDC. Once we know that we have the correct device, and we make sure that everything is dismounted, so we will make sure that sudo umount, because we do not want to be writing to a mounted file system. In this way, this will cause a whole slew of problems, and you do not want to write to this SD card while it is mounted. Notice SDC1 and SDC2 are not mounted. Actually, if we change the language here. So let's copy paste the command to write this, and like I mentioned before, this is on the blog post, and I will provide a link to this blog site in the description, which will include the entire script that I'm using to copy paste these commands from. We'll copy up to this /dev portion here, paste this in the command window, and we have /dev/SDC. And we want to be writing to SDC, not SDC1 or SDC2, because we're going to rewrite the entire file system on the SD card. If we write to SDC1 or 2, it will be writing to the individual partitions on the SD card, which is not what we want. And I am actually not sure what will happen if we do that. The SD card file system will not be properly set up. So we'll go ahead and write this to the SD card, and this will take a few minutes, depending on the speed of the SD card. We will come back in a minute when that write's completed. Okay, SD card write has finished. Let's do a sync to make sure that everything is flushed and written to the SD card and not sitting in the buffer. Once that's done, we can remove the SD card from the computer, and we will set up the Raspberry Pi. So what we've got for the Raspberry Pi, so we've got our freshly written SD card, and I will put it in this case, although not necessary. So you've got our fan. Fan connects right there. Okay, we're going to leave the lid off. Okay, we've got a number of things to connect. Now, I am going to be using a wired network connection for this, just to not have to mess with the Wi-Fi setup. Connect that. We've got our mouse and keyboard. Actually, connect this stuff first. This is our power. We'll connect that last. We have our video cable for our display. I'll plug it in this micro HDMI port. And that should be everything. So let's, oh, we forgot the hard disk. Let's connect up the hard disk. We'll attach it after the Raspberry Pi initial setup is done. We can go ahead and plug in the power to the hard disk. This is a spinning disk, so you do want to be careful. I don't want to jolt the thing as it's on. It's probably not a good idea to move it around either. So we'll kind of leave this disconnected for now, and I will get the Raspberry Pi. Let's see, let's connect the video cable up. So let's start up the Raspberry Pi the first time with this new SD card, and we will get the initial setup knocked out really quick, then we can move on to our kernel building. Okay, next. Language selection next. Now I might get a lot of comments about this, but we're just going to use the default Raspberry Pi username and password since this Raspberry Pi isn't going anywhere. Just use the Pi and Raspberry for the password. And it is going to complain. That's okay. We'll skip the Wi-Fi setup since we have a wired internet connection connected up. Yes, I like Firefox. Go ahead and let it do a software update. Okay, software update is done. And we'll restart the Raspberry Pi. Okay, so we have our Raspberry 5 rebooted, and we're going to connect our external SSD hard disk now and prepare the external hard disk for the kernel build. So we connect the external hard disk. So for this project, I'm going to be using the second partition on the hard disk. I have a number of other projects on this hard disk, so we will designate the second partition for this project. So the first thing I want to do is clean the partition off. And the partition that I'm going to be using, go df-h, we can see what I've got. And what I would like to use is SDA2. So we're going to dismount the partition. SDA2. And I'm going to format the partition quickly. Now when you do format a partition, you want to make sure it's unmounted. If you format a mounted partition, you will create a mess, something that you probably do not want to do. So we'll do makefs.ext4. And our target will be /dev/SDA2. And it's going to warn us that there's an existing file system. So we'll go ahead and proceed with the format. And the format is complete. So we'll go ahead and dismount the other partitions. And we'll just disconnect the hard disk and plug it back in to auto mount all the partitions, including the one that we just prepared. And everything remounted. And just to confirm, we can look at mount, or we can look at DF. I noticed that SDA2 remounted, and it's now available for us to use for this project. So a lot of these commands for the kernel build, I'm just going to be copy pasting from my blog site that I wrote up earlier on this project, and the kernel build is just going to be just a straight copy paste of all those commands. So I will provide a link in this video's description, and you can open up the blog site and download the file and follow along. So open up the blog site. It is the first post, or at least now it is the first post, Raspberry Pi 64-bit kernel, Linux kernel rebuild. If we scroll down, I have most of the commands in the blog post itself, but we're going to download the text file, which is just easier to copy paste. So we'll open that up. And there's a couple things that we need to set up off the script file immediately. The first thing is, let's go ahead and drop into super user mode. It'll make executing a lot of these commands a lot easier. And we won't have to precede each command with sudo. And we'll need to update a couple things. I use environment variables throughout this script, and it helps with if needing to update any part of the environment variables or any of the folders and paths used. It's easier to just update one of these variables versus doing a copy paste on the entire document. So the first thing we need to update is the work root, which is our external USB device. Now we could, if we wanted to, we could use the internal SD card for this, but like I said, if we set it to home/pi, which is our current home directory for the Pi user that's logged in now, we're going to hammer this SD card and we're probably going to wear it out. So I would recommend against doing that and use an external hard disk if you can. So we'll go ahead and copy and paste this path into the work root, and we'll see the work directory is derived from the work root, and the work directory is going to be kernel build, and it's going to be and it's going to have the current date appended to the end of it. Now I'm also appending the date to the end of a lot of these file names and such, and we'll see this generated with this date command. If you'd like to fix this date, I mean, you could just change this to, say, if you just wanted to 2025, say January 13th, and you just want to fix it to that timestamp, you can do that, but we're just going to have the script pull it from the date command. And there's two other variables we need to look at, which is the boot directory and the kernel modules directory. And these are only important for when we actually update the kernel on the SD card. So if you want to verify that we get the boot directory correctly, we could just take a look at the boot. So if we change directory to /boot and we take a look at it, we'll notice that it has changed a little bit. And if we look at one of these files, say config.txt, and we'll notice that it's been moved. And we can indeed confirm that by looking at mount and seeing that indeed the boot partition has been moved to /boot/firmware. That is where it's mounted now. And we can also see this same information by going into df and seeing it's under boot/firmware. So that is going to be the boot partition that we will update. And the kernel modules this is just the general path that's usually the same for most Linux installations. And this is basically the drivers for the kernel that are not compiled into the kernel itself. These will need to be updated because they are specific to the kernel version that is being run. Once this is done, we'll go ahead and copy paste this into terminal and set these variables. Now you'll notice throughout this document, I'm going to be copy pasting this, and I'm going to be pushing the right mouse button, I'll be pushing the middle button on the mouse. That's a trick in Linux to copy paste something that's selected. And the next command will basically clear out the work directory if any existed before, and this is on our external USB device. And then there are some additional build tools that are required that are not normally installed on the Raspberry Pi using the when the SD card is created, so we will need these tools for performing the build. We'll go ahead and let it download and update those tools. Okay, those tools have been installed. And the next step is we're going to download the Linux kernel source tree, and this is going to be the Raspberry Pi fork. And the differences between this and the the base kernel, the original kernel is Linux kernel, is that the Raspberry Pi team has made some patches that fix various quirks and glitches on the Raspberry Pi for their flavor of the Linux kernel, so we will use that. So first it's going to clean out the existing download if we had any, and then it's going to use git to clone the source tree onto our USB hard disk. So it'll take just a second to download. Now while that's downloading, so I'll explain some of these next commands. So one thing that I would like to do is I'd like to keep track of the Linux kernel version. And the Linux kernel version is actually located in the makefile at the top. And these commands right here is just a fancy way of automatically parsing that information and throwing it into this kernel version environment variable. So once this is done downloading, I will open up that makefile and show you where those variables are. And just executing these lines here will pull that information automatically. Okay, so if we want to check out our download, this is the Linux source tree. And if we look at the makefile, like I said earlier, we'll notice at the top of the file we have version, patch level, and sub level. And this is the information that we're going to pull to keep track. So the version of the kernel would be 6.6.70. So going back to here, we'll copy paste this in, and this will automatically pull that information out of the makefile. And then we're going to use tar. We're going to create a zip archive. I'm going to do this throughout the build. I will make archives as we go through different steps of the process, and it will allow us to easily recover anything if we tend to mess up a file or anything. This will also give us an archive of the current state or the current download that we have in case we need to reference it in the future. This will take just a second to create the tar file. It is basically just creating an archive, like a zip file, with a full directory structure in it of the kernel that we just downloaded. And while that is downloading, so the Raspberry Pi, actually we have two different kernel configurations that we'll have to deal with. The Raspberry Pi 5 uses a slightly different kernel configuration than the Raspberry Pi 4s and before that. We're only dealing with the 64-bit version of the kernel. So we will have to do two builds, which isn't too bad, but we'll do two builds so that we support both the Raspberry Pi 5 and the previous Raspberry Pis that are 64-bit as well. Check the status of this. This will take a minute to complete. Okay, and all this work that we're doing, all this work is being done on the external hard disk. We are not touching the Raspberry Pi file system except for the build tools that we did the apt-get, the apt install to install previously. Okay, it looks like we're about done, hopefully. All right, the archive has been completed. So we're going to go ahead and set up for, we'll go ahead and set up for the configuration of the kernel. So we're going to go change the, we'll just copy paste these commands in. Notice that a lot of this stuff in this document, anything that starts with 3 stars is kind of a comment. Anything with a pound sign in front of it is also a comment. So what we're going to do is we're going to change to the kernel source. Then we're going to set the kernel version, which is going to be kernel 8. And this environment variable kernel, this is used in various places to rename files and such. And this make bcm2711 def config, this creates a default config, which is a pre-setup configuration for the Raspberry Pi. Now, for a project that I'm working on, there's one change that I would like to make to the kernel. And this default configuration will work in most cases, but in my case, I would like to make a change to the configuration, and we can easily do that using something called menu config. If we open up menu config, we do a make menu config. And the thing that I want to add to this is the BTRFS file system support. While the Raspberry Pi Linux kernel does have that support built in, it's built in as a kernel module, which is located on the root file system, which means that if I want my root file system to be in BTRFS format, it needs that driver available before the root partition is mounted. And the only way to get that to happen is to have the driver built into the kernel itself, not as a module. So that's the change that I'd like to make. So looking at this, so if we go down to File System, and we scroll down, and we'll find BTRFS File System Support. And we'll notice that built in as a module. If we push Y on the keyboard, we can change that to an asterisk, which means that it will be built into the kernel itself, which will increase the size of the kernel slightly, but it will also mean that the BTRFS file system support will be available before the root file system is mounted, which is what I need for a project that I'm working on. So we'll do an exit, and we'll save the configuration. And there is an option that you can change the local version of your kernel. I will not do this, but it is possible to customize the name of the kernel that displays. And I'll give an example that if we do a cat proc/version, this is the current kernel that's currently on the Raspberry Pi right now. This will allow you to alter the information displayed here. So the next step is going to take a while. This is going to be the actual compile. So this will compile everything. So we're going to do make/6g tells the compiler to use 6 threads. And image.gz, that's what we're going to be compiling. And then we're also going to compile the modules and the DTBS, which are the overlay files for the Raspberry Pi. So we'll copy paste this into the command window, and we'll let this thing go. And this may take 30 minutes to an hour or more to run. I recommend you run this on a Raspberry Pi 5 if possible. It will be a little bit slower on a Raspberry Pi 4. There are methods that you can cross-compile this, but in order to just not mess with the quirks and possible issues with cross-compiling, I'm just going to compile this on the Raspberry Pi at the time. So this will take a while. I will come back to the video. When we finish up this compiling. All right, so the compile finished, and so the next thing that we need to do is we need to copy out the kernel modules. The kernel modules are basically the drivers for the system that are not compiled directly into the kernel. and the kernel will load them off the root file system as they are needed. So we'll go ahead and copy those out using the next commands. And this will take just a minute. Okay, the kernel modules are copied out, so let's go ahead and archive them. Now, when I do this, normally when you do the modules install here, if you do not put the install mod path in here, it will drop the modules directly into your lib modules folder. And in this case, we specify where we want them to be dropped so that we can archive them and copy them in ourselves later. So next we're going to archive the modules off into a tar file. Okay, and then finally we're going to archive the kernel for later use in another tar file. So I'll copy paste these commands. And then we're also going to archive the overlay files for the Raspberry Pi. And also, as we're archiving these, we're also archiving the config file as well so that we can recreate this kernel configuration, or we can go back and look at it any time to see how we configured our kernel. So the next step, after we compiled the kernel configuration for the Raspberry Pi 4 and lower, so for the next step we need to compile the kernel configuration for the Raspberry Pi 5. And we will do that by executing these next few commands, and this is the kernel 2712. So we'll reconfigure the kernel source tree to build this configuration. And just like before, we are going to add in the BTRFS support into compiling into the kernel directly. Now, you don't have to do this, this is optional, but for a project that I'm working on, I would like to have this available for the root file system. So we'll go ahead and change this to a yes, and exit, exit, save. While we're in there, we could change any other configuration options that you would like to configure as well. Okay, the kernel compile is configured, so we will, just like the other compile, we'll just run the make command. And this will take 30 minutes to an hour, somewhere around there, and we will come back when this is complete. All right, after quite a bit of compile time, we have finished the compile. So let's do the same thing that we did with the other compile, and we will run the kernel modules. Then we will archive the modules for later use. As soon as this finishes. Okay, let's copy paste this in. Kernel modules are archived. Let's go ahead and archive the kernel itself and the config. And we will archive the overlays. The overlays should be the same between both the kernel compiles. We will archive them anyway. Okay, up until now, if we go back to our working folder, we'll notice that we have created a bunch of files in the process. We have the Linux kernel, we have the sources here that we archived, the first thing that we archived. then these are the directories that we created during the process. This is the kernel 2712. This contains all the files before we archived things. And we've got the kernel 8, which is the first compile that we did. So if we look at some of these directories, I mean, this is basically the result of the script we executed. We'll notice it has our config and it has our image file. These are the results of the compile that we did. And then finally we have the modules and the module archives and the overlays. So up until this point, we are basically done. We've compiled the kernel. The next step involves updating the kernel on the actual Raspberry Pi if you'd like to do that, and that's what the next steps will do. Now, while this step is not necessary, I'm going to create an archive of the current file system on the boot partition of the Raspberry Pi. This will allow us to recover from it if we end up messing things up. So this is going to be the current backup of what is on the the boot folder right now, and we can take a look at this. So after this backup finishes, we'll take a look at what we just backed up. That's essentially this boot directory. This is essentially what we just backed up. Now, these next commands, we are not going to execute this. This is just a simple way to recover that boot directory. Basically, is going to wipe everything out, and it's going to recover the boot partition from our backup. You don't want to execute this. Definitely, if you do this, make sure that this command is completed entirely before you attempt to reboot the Raspberry Pi. While the kernel is loaded in memory, so it does not require what is on the boot partition while the system is booted, but when you reboot it, it will require it. Okay, the next commands that we're going to execute will actually update the kernel on the Raspberry Pi. The first one is going to be the Raspberry Pi 4 and lower kernel. So we will execute this command. What this is going to do is this will copy from the archive that we created for the kernel 8 into the boot partition. Okay, and then we're going to also update the overlay files. And we're also going to update we're going to copy the kernel configuration in. While this is not required, this will allow us to see later on down the line if we want to take a look at how we configured the kernel on the compile. And this is a good idea to save this as well, and we will make this available on the boot partition. So if we look at the current boot partition, what we just updated, and we'll notice we have a kernel 8 config now in here. And then we're going to do the same thing for the kernel. Now we're not done yet. We need to copy the kernel modules in, which are the drivers. If we stop here, we will not have the modules in, which is the drivers for the new kernel, and there will be numerous problems when we restart the Raspberry Pi. Like I said, the overlays will probably be the same, so we will skip those. And then we're going to copy in the kernel configuration as well. Now, we are going to update the modules, and the modules should be located in /lib/modules. And we could take a look and see what's in there right now. And we have 6.6.51, 6.651. These are the two kernel modules for the two kernels that are currently on the Raspberry Pi. And we are going to add to that our kernel modules that we just created. Now, once we update the kernel, you actually do not need to retain these, and these could be deleted if desired, but we're going to leave them there just in case. So go ahead and update those kernel modules. And when we are done here, we'll take a look at this folder. And we'll notice that we have two more folders created, which is 6.6.70 for the V8 and for the V8 16K, which are the two kernel configurations that we created. At this point, we have actually updated the Raspberry Pi, so we're going to do a restart on the Raspberry Pi. We can do a restart right from the command prompt by doing a shutdown -R now, or we can execute it from the GUI here. So we'll go ahead and do a reboot, and if everything worked correctly, the Raspberry Pi will start up with the new kernel. And it looks like the Raspberry Pi started up correctly. So we'll go ahead and open up that script that we downloaded previously and have been working off from. And we'll go ahead and check the kernel version that's currently running now. So at the bottom of the script, we'll notice we have a command here to check that, and actually there's a mistake on here. There should be a cat in front of here, so I will correct that on the document and re-upload it. So go ahead and copy and paste this into the terminal window, and we will see that our current running kernel is now version 6.6.70. We see the user that compiled it, and we see the compile time of this kernel, which is January 13th, 2025. And if we would like, we can take a look at the all this stuff that we compiled. And let's pull up the hard disk, our external hard disk. So we'll go ahead and change directory to here. If we take a look at this, we have a kernel build here. So this is the result. These are all the archived results from the kernel build, and like you could see, this is pretty much how long it took to run through this entire process. So it looks like we started at least the kernel sources were archived at 8:40 p.m. and finally, what time is it now? Oh, that time's not correct. The last time that we have here is 10:14, looks like 10:16 p.m. So that's a few hours. So we have the bootfs, which is the archive of the boot file system, and then of course we have the backup of the kernel sources, the original tree before we did any configuration changes to it. And then of course we have the archives of the kernel we created, the overlays, the modules, and the same for the kernel 8, which is for the Raspberry Pi 4 and below. So with that, I believe this wraps up the kernel rebuild, and hope that this was useful information, and we'll see you on the next video. Thanks for watching.